Welcome to Dreamly Sleep Space. I'm so glad you're here tonight. This is a place where curiosity meets calm, where the wonders of our world become a gentle path toward rest. Perhaps your day was full, perhaps your mind is still turning, or perhaps you simply love drifting off to the quiet voice of exploration. However you arrived, you're welcome here. Tonight's journey takes us into black holes, those mysterious points in space where gravity becomes so overwhelming that not even light can escape. They are places where time bends, where the fabric of the universe curves back on itself, and where our understanding of physics reaches its most profound limits. You don't need to do anything but listen and let go. If these journeys help you find peace at the end of your day, consider subscribing to Dreamly Sleep Space. It helps others discover this quiet corner of the night. Now, close your eyes if you wish, and let us drift together toward the darkest, most fascinating objects in all, the cosmos. Black holes are regions of space-time where gravity has become so intense that nothing within a certain boundary can escape, not matter, not light, not even information itself. They represent one of the most extreme predictions of Albert Einstein's general theory of relativity. Published in 1915, Einstein's equations described how massive objects warp the fabric of space-time around them, creating what we experience as gravity. But even Einstein himself found it hard to believe that nature would allow something as extreme as a black hole to exist. The story begins not with darkness, but with light. Every star in the night sky is a delicate balance, a battle between two fundamental forces. Gravity pulls inward, trying to collapse the star. Nuclear fusion in the star's core pushes outward, generating heat and pressure that resist that collapse. For millions or billions of years, this balance holds. The star shines, steady and bright, converting hydrogen into helium, helium into carbon, carbon into heavier elements. It is a cosmic forge, creating the very atoms that will one day form planets, oceans, and perhaps even life itself. But nothing lasts forever. Eventually, even the most massive stars exhaust their nuclear fuel. When the fusion stops, the outward pressure disappears, and gravity, patient and inexorable, finally wins. What happens next depends on the mass of the star. For stars like our Sun, the end is gentle. They swell into red giants, shed their outer layers, and settle into quiet retirement as white dwarfs, small, dense embers slowly cooling over trillions of years. For more massive stars, between 8 and perhaps 20 times the mass of the Sun, the collapse is more violent. The core implodes, then rebounds in a catastrophic explosion called a supernova. What remains is a neutron star, a sphere perhaps 20 kilometers across, but containing more mass than the Sun, where matter is compressed to densities found nowhere else in nature, except inside atomic nuclei. But for the most massive stars, those born with more than about 20 to 25 times the Sun's mass, even neutron degeneracy pressure cannot halt the collapse. These stellar giants, having fused elements all the way up to iron in their cores, face a moment of inevitability. Iron cannot be fused to release energy. It is the end of the line. When the core collapses, nothing can stop it. In less than a second, sometimes in just a tenth of a second, the core of the star compresses past the point of neutron star density and continues falling inward. It shrinks beyond any known physical state of matter. Protons and neutrons break down into their constituent quarks. Even quarks may dissolve into something more fundamental, something we do not yet have names for. The collapse continues until all the mass of the stellar core is concentrated into a region of infinite density and zero volume, a point called a singularity. And around that singularity, space-time itself is warped so severely that a boundary forms. This boundary is called the event horizon. Once anything crosses that threshold, moving inward toward the singularity, it can never return, not with rockets, not with any force imaginable. Even light, traveling at the ultimate cosmic speed limit, cannot climb back out of the gravitational well. The region within the event horizon becomes invisible to the outside universe. It becomes, quite literally, a black hole. This is how stellar mass black holes are born, in the violent final moments of a massive star's life. But there are other ways for black holes to form. In the dense cores of ancient globular clusters, where thousands of stars are packed into a small region of space, stellar mass black holes can collide and merge, growing larger with each union. Sometimes, neutron stars spiral together over billions of years, their orbits gradually decaying as they radiate gravitational waves. When they finally touch, in a collision lasting mere milliseconds, they can merge to form a black hole, releasing more energy in that brief instant than all the stars in a galaxy combined. Or perhaps a neutron star, quietly orbiting a companion, slowly pulls gas from that companion's outer layers. Over time, the neutron star gains mass. When it crosses a critical threshold, about 2 to 3 times the mass of the Sun, the neutron degeneracy pressure that has supported it for eons suddenly fails. The star collapses in on itself, and a new black hole is born, not in a dramatic explosion, but in near silence, a implosion rather than a supernova. Not all black holes announce their arrival with light and fury. Recent observations have found massive stars that simply vanished from the sky, collapsing directly into black holes without any visible supernova at all. The collapse releases its energy not as light, but as neutrinos, ghostly particles that slip through matter almost unnoticed. To distant observers, the star simply fades away, as if a curtain has been drawn across a window. Only later, when astronomers return to check on the star, do they find empty space where light once shone. A black hole has formed in darkness, swallowing even its own birth announcement. These are the pathways by which nature creates black holes from stars. But they are not the only pathways. In the hearts of galaxies, in the first moments after the Big Bang, through mechanisms we are only beginning to understand, black holes form in other ways, and once formed, they are remarkably simple objects. According to a theorem in general relativity called the no-hair theorem, a black hole can be completely described by just 3 properties: its mass, which determines the strength of its gravitational field, its electric charge, though most black holes are thought to be electrically neutral because charged matter is so easily neutralized in space, and its angular momentum, or spin, because most stars rotate, and when they collapse. Conservation of angular momentum means the resulting black hole spins as well, often at extraordinary speeds. Everything else about the star that formed the black hole is lost. Its chemical composition, its magnetic field, the detailed history of its life, all of that information is erased. The black hole retains only mass, charge, and spin. It is, in a sense, the ultimate minimalist object, stripped of all detail, reduced to pure geometry. And yet, despite this simplicity, black holes remain among the most complex and puzzling objects in the universe. To understand why, we must look more closely at their structure, at the strange boundary that defines them, and at the even stranger region within. The event horizon is perhaps the most important feature of a black hole, yet it is not a physical surface. You could not stand on it, you could not touch it. If you fell toward a black hole, you would pass through the event horizon without feeling anything unusual at that precise moment, at least not from the horizon itself. It is simply the mathematical boundary where the escape velocity equals the speed of light. Escape velocity is the speed you would need to escape from the gravitational pull of an object without using any additional propulsion. On Earth, the escape velocity is about 11 kilometers per second. On a neutron star, it can be half the speed of light. At the event horizon of a black hole, the escape velocity is exactly the speed of light, And since nothing can travel faster than light, nothing inside the horizon can escape. The size of the event horizon is determined by the black hole's mass. In 1916, just months after Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild found an exact solution to Einstein's equations for a non-rotating, spherically symmetric mass. This solution gave a precise formula for the radius of the event horizon, now called the Schwarzschild radius, in honor of the man who discovered it while serving in the German army during World War I. Schwarzschild sent his solution to Einstein, who was astonished that such a precise answer could be found. Tragically, Schwarzschild died shortly after from an autoimmune disease contracted at the front, never knowing how profoundly his work would shape our understanding of the universe. The Schwarzschild radius depends only on mass. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it is about 9 millimeters. These numbers tell us how much we would need to compress these objects to turn them into black holes. The Sun would need to be squeezed into a ball 6 kilometers across. Earth would need to fit inside a marble. For a stellar mass black hole, born from a star perhaps 10 times the mass of the Sun, the event horizon would have a radius of about 30 kilometers. That is smaller than most cities. Yet within that region, there is more mass than in our entire Sun, compressed beyond imagination. For a supermassive black hole, the kind found at the center of galaxies, with a mass millions or billions of times that of the Sun, the event horizon can be vast. Sagittarius A*, the supermassive black hole at the center of our Milky Way galaxy, has a mass about 4 million times that of the Sun. Its event horizon has a radius of about 12 million kilometers, roughly 17 times the radius of the Sun. If you could somehow place Sagittarius A times where our Sun is, its event horizon would not quite reach the orbit of Mercury. The supermassive black hole at the center of the galaxy M87, one of the first black holes ever directly imaged, has a mass of about 6.5 billion times the Sun. Its event horizon is so large that it could contain our entire solar system out past the orbit of Pluto. And yet, even this enormous region is utterly dark, invisible, defined only by the glowing ring of hot gas that surrounds it. Inside the event horizon lies the singularity, the point where all the black hole's mass is concentrated. According to general relativity, this is a region of infinite density, where space-time curvature becomes infinite, and where the laws of physics as we currently understand them break down completely. At the singularity, our equations produce infinities, nonsensical answers that suggest we are asking the wrong questions or using the wrong tools. Most physicists believe that singularities are not real in the literal sense. They are a sign that general relativity, magnificent as it is incomplete. At the extraordinarily small scales and immense densities of a singularity, quantum mechanics must play a role. We need a theory of quantum gravity, a framework that unites Einstein's description of space-time with the quantum nature of matter and energy. But despite decades of effort, we do not yet have such a theory. The singularity remains a mystery, hidden behind the event horizon, inaccessible to observation. Between the event horizon and the singularity, space-time is so warped that the roles of space and time are reversed. Outside the horizon, you can stand still in space and move forward in time. Inside, the singularity lies in your future, not in a particular direction in space. Moving toward the singularity is as inevitable as moving forward in time. No matter which direction you point, no matter how you accelerate, the singularity draws closer with every passing moment. Inside the event horizon, falling into the singularity is not a choice. It is simply what happens next, as unavoidable as the next tick of a clock. For a rotating black hole, the structure becomes even more intricate. Rotation drags space-time around with it, creating a region called the ergosphere, just outside the event horizon, where nothing can remain stationary. Everything within the ergosphere is forced to rotate in the same direction as the black hole, caught in a current of spacetime itself. The Bose event horizon of a rotating black hole is oblate, bulging at the equator, and the singularity is thought to be not a point but a ring, a loop of infinite density rotating in the equatorial plane. These rotating black holes, described by the Kerr solution to Einstein's equations, are likely the most common type in the universe. Most stars rotate, and when they collapse, conservation of angular momentum means they spin faster, like a figure skater pulling in their arms. Some black holes may spin at nearly the maximum rate allowed by physics, their event horizons whirling around hundreds of times per second. But whether rotating or not, whether massive or small, all black holes share the same fundamental architecture. A singularity at the center, hidden from view, an event horizon marking the boundary of no return, and surrounding them, often, a glowing disk of matter spiraling inward to its doom. Black holes come in different sizes, born through different mechanisms, scattered across the universe in numbers we are only beginning to comprehend. The smallest and most common are stellar mass black holes, the remnants of massive stars. These typically range from about 3 times the mass of the Sun to perhaps 50 or even 100 solar masses. Astronomers have identified dozens of these objects in our galaxy alone, usually by observing how they affect nearby companion stars. The black hole itself is invisible, but its gravity pulls gas from the companion, and that gas heats up as it spirals inward, emitting X-rays that we can detect from Earth. In 2015, the LIGO gravitational wave detectors made a groundbreaking observation. They detected the ripples in space-time produced by 2 stellar mass black holes, one about 29 solar masses and the other about 36 solar masses, spiraling together and merging. In a fraction of a second, they formed a single black hole of about 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves. This was the first direct detection of gravitational waves, confirming a major prediction of general relativity and opening a new window onto the universe. Since then, LIGO and its partner detectors have observed dozens of these mergers. Some involve black holes more massive than we thought stellar collapse could produce, raising questions about how they formed. Perhaps they are the products of previous mergers, black holes that have already swallowed other black holes and grown larger. Or perhaps they formed in the early universe through mechanisms we do not yet understand. The largest black holes in the universe are supermassive black holes, found at the centers of most large galaxies. These monsters can have masses ranging from hundreds of thousands to tens of billions of times the mass of the Sun. Our own galaxy, the Milky Way, harbors a supermassive black hole called Sagittarius A*, with about 4 million solar masses. The galaxy M87 has one of the most massive black holes ever measured at 6.5 billion solar masses. And in 2024, astronomers announced the discovery of an even more massive black hole, perhaps 40 billion solar masses, lurking in the heart of a distant galaxy. How supermassive black holes form remains one of the great mysteries of astrophysics. They cannot be the products of single stellar collapses. No star is massive enough to leave behind a billion solar mass black hole. Instead, supermassive black holes must grow over time, either by swallowing gas and stars, or by merging with other black holes, or perhaps both. One possibility is that they start as seeds, smaller black holes formed in the early universe, perhaps just hundreds or thousands of solar masses, and then grow by accreting matter over billions of years. Another idea is that in the very early universe, giant clouds of gas collapsed directly into massive black holes without ever forming stars first. These direct collapse black holes could have provided the seeds that grew into the supermassive black holes we see today. Observations with the James Webb Space Telescope have found supermassive black holes in galaxies less than 1 billion years after the Big Bang. This is puzzling. These black holes are already billions of solar masses, yet they have had relatively little time to grow. How did they get so big so fast? This is one of the questions driving current research, and the answers may reshape our understanding of how galaxies and black holes co-evolve. Between stellar mass and supermassive black holes lies a mysterious gap. For many years, astronomers searched for intermediate mass black holes, objects with masses between 100 and 100,000 times the Sun. These should exist if supermassive black holes grow through mergers, starting small and building up over time. Yet intermediate mass black holes proved elusive, difficult to detect and confirm. In recent years, evidence has mounted. Gravitational wave detections have revealed black holes in this mass range, formed from the merger of smaller black holes. Observations of dense star clusters suggest that intermediate mass black holes may lurk in their centers, their gravity stirring the motions of nearby stars. And in some galaxies, fast-moving stars near the core hint at the presence of a black hole too massive to be stellar, yet too small to be supermassive. These intermediate mass black holes may be the missing links in the story of black hole growth, the stepping stones between stellar remnants and galactic behemoths. Finding more of them and understanding how they form and grow remains an active area of research. And then there are primordial black holes, objects that may have formed in the first fraction of a second after the Big Bang. In that earliest instant, before the universe had expanded and cooled, fluctuations in density might have been so intense that regions of space collapsed directly into black holes without needing the mass of a star or galaxy. These primordial black holes could have a wide range of masses, from far smaller than an atom to thousands of times the mass of the Sun. If they exist, they might account for some or all of the dark matter that makes up most of the mass of the universe, or they might explain how supermassive black holes formed so quickly in the early universe. But primordial black holes remain hypothetical. No one has conclusively detected one. Searches continue, using gravitational lensing, gravitational waves, and other techniques. If they exist, and if we find them, they could answer some of the deepest questions in cosmology. If they do not exist, that too would teach us something profound about the nature of the early universe. Whether primordial or stellar, intermediate or supermassive, all black holes share one quality. They reach out across space and time, pulling on everything around them, bending light, warping spacetime, and shaping the structure of the cosmos in ways both visible and hidden. Gravity is the defining feature of a black hole, the force that creates it and the force it wields. Near a black hole, gravity becomes so strong that it dominates everything, overwhelming all other forces, sculpting the motion of matter and light in ways that seem impossible, yet are precisely predicted by general relativity. The gravitational pull of a black hole follows an inverse square law, like that of any massive object. Move twice as far away, and the force is 1/4 as strong. Move 10 times farther, and it is 1/100th as strong. Far from a black hole, its gravity is no different from that of any other object with the same mass. If the Sun were suddenly replaced by a black hole of equal mass, the planets would continue in their orbits unchanged. The Earth would not be sucked in. The black hole's gravity at the distance of Earth would be identical to the Sun's gravity. But close to the black hole, within a few times the Schwarzschild radius, gravity becomes overwhelming. Matter that ventures too close is pulled inward, accelerating to immense speeds. As it falls, it collides with other infalling matter, and these collisions generate heat. The temperature rises until the matter glows, first red, then orange, then white-hot, and finally emitting X-rays and ultraviolet light. This glowing matter forms an accretion disk, a swirling whirlpool of superheated gas spiraling toward the event horizon. Accretion disks around black holes are among the most energetic phenomena in the universe. They can outshine entire galaxies, visible across billions of light years. The light comes not from the black hole itself, which remains dark, but from the friction and collisions in the disk, from matter converting its gravitational potential energy into heat and light as it spirals inward. Some of this matter reaches the event horizon and disappears forever, but much of it is ejected before it crosses the supporter horizon, blown outward by powerful magnetic fields and radiation pressure, forming jets that stream away from the black hole at nearly the speed of light. These jets can extend for thousands or even millions of light years, carving out vast cavities in the surrounding gas, triggering star formation or suppressing it, sculpting the evolution of entire galaxies. They are one of the ways black holes reach out and affect their environment, even though the black hole itself remains hidden behind its event horizon. The gravitational field around a black hole also produces tidal forces, differences in gravitational pull from one place to another. If you were to fall toward a black hole feet first, your feet would be closer to the black hole than your head, and so they would experience a stronger pull. This difference in force would stretch you lengthwise while simultaneously compressing you from the sides. As you fell closer, the tidal forces would grow stronger. Your body would be stretched thinner and thinner, like a piece of spaghetti, in a process astrophysicists whimsically call spaghettification. For a stellar mass black hole, these tidal forces would become lethal well before you reach the event horizon. Your body would be torn apart by the difference in gravitational pull. But for a supermassive black hole, the tidal forces at the event horizon are surprisingly weak. The larger the black hole, the gentler the tidal gradient at the horizon. For a black hole of 1 billion solar masses, you could cross the event horizon and survive, at least for a while. You would feel no particular sensation at the moment of crossing. Only later, as you fell deeper and the tidal forces grew, would spaghettification become a concern. By then, of course, it would be too late. You would be inside the event horizon, with no way to escape, falling inevitably toward the singularity. Stars can suffer a similar fate. If a star passes too close to a black hole, the tidal forces can overcome the star's own gravity, pulling it apart in an event called a tidal disruption. Astronomers have observed several of these sudden bright flares as a star is shredded and its gas heats up while spiraling into the black hole. The flare can last for months or years, a temporary beacon marking the star's destruction. The gravitational field of a black hole also affects light itself. Light passing near a black hole is bent by the curvature of spacetime, a phenomenon called gravitational lensing. If a black hole passes between us and a more distant star, the black hole's gravity can bend the star's light, causing the star to appear to shift position or brighten temporarily. Astronomers have used this effect to detect black holes that would otherwise be invisible, dark wanderers drifting through space. Light emitted near a black hole, trying to escape the intense gravitational field, must expend energy to climb out. This energy does not come from the light slowing down. Light always travels at the same speed. Instead, the light loses energy by becoming redshifted, its wavelength stretching, its color shifting toward the red end of the spectrum. The closer to the horizon the light originates, the more it is redshifted. Light emitted right at the event horizon would be redshifted to infinitely long wavelengths, effectively losing all its energy. It would never reach a distant observer. This gravitational redshift is one reason why black holes are black. Even if there were a glowing surface at the horizon, its light would be redshifted away to nothing. Around rotating black holes, spacetime is not only curved but also dragged around in the direction of the black hole's spin. This effect, called frame dragging, means that anything near a rotating black hole is pulled along with it. You could not remain stationary, even if you tried. The rotation of spacetime would force you to orbit, whether you wanted to or not. These gravitational effects, tidal forces, lensing, redshift, frame dragging are all predictions of general relativity, and all have been observed, confirming that black holes behave exactly as Einstein's theory predicts, even in these most extreme conditions. One of the strangest effects of a black hole's gravity is its influence on time itself. According to general relativity, time does not flow at the same rate everywhere. It is not an absolute, universal clock ticking uniformly throughout the cosmos. Instead, time is relative, flexible, flowing more slowly in strong gravitational fields and speeding up where gravity is weak. This phenomenon is called gravitational time dilation. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers. One is floating safely far from a black hole, far enough that the gravity is weak and time flows normally. The other is near the event horizon, hovering just above the point of no return. For the observer near the horizon, time passes at its usual pace. Their watch ticks normally. Their heart beats as it always has. From their perspective, nothing is unusual. But from the perspective of the distant observer, something extraordinary happens. They watch the clock of the observer near the horizon, and they see it ticking more slowly. The light from that clock is redshifted, stretched to longer wavelengths, its frequency reduced. If the nearby observer waves, the distant observer sees the wave in slow motion, as if time itself has thickened. The closer to the event horizon, the more severe the effect. At the horizon itself, from the distant observer's viewpoint, time slows to a stop. An object falling toward the horizon appears to slow down, moving more and more sluggishly, never quite reaching the boundary. Its light becomes dimmer and redder, fading from view. To the distant observer, it looks as if the object is frozen just above the horizon, trapped in a moment that stretches on forever. This is why, in the early days of black hole research, some scientists referred to them as frozen stars. From outside, the collapse of a star into a black hole appears to take an infinite amount of time. The surface of the star seems to freeze at the Schwarzschild radius, never quite crossing over. But this is only how it looks from a distance. For someone falling into the black hole, the experience is entirely different. From their perspective, time flows normally. Their watch ticks at its usual rate. They cross the event horizon in a finite amount of time, perhaps in just a few seconds for a stellar mass black hole or a few hours for a supermassive one. They feel no sudden jolt, no wall, no barrier. The horizon is not a physical place. It is simply a mathematical boundary, and they pass through it as smoothly as a ship sailing over an invisible line on the ocean. Once across, they continue falling. The singularity lies ahead, growing closer with every passing moment. For a stellar mass black hole, the time from horizon to singularity might be just a fraction of a second. For a supermassive black hole, it could be hours, even days. But the outcome is the same. Eventually, they reach the singularity, and there, our understanding ends. This difference in perspective between the distant observer and the infalling one is one of the most profound features of black holes. It highlights the relativity of time, the way it bends and flows differently depending on where you are and how you are moving. There is no single, universal now. Different observers in different gravitational fields experience time differently. What appears as frozen to one may be flowing to another. This time dilation has been measured, not at black holes, which are too far away, but in gentler gravitational fields. Atomic clocks at the top of a building run slightly faster than identical clocks at the bottom because the gravity is weaker higher up. GPS satellites must account for gravitational time dilation. Their clocks tick faster than clocks on Earth's surface. And if this effect were not corrected, GPS positioning would become inaccurate within hours. The time dilation near black holes is just an extreme version of the same phenomenon, and it leads to strange thought experiments. If you could hover near the event horizon of a supermassive black hole for a while, then return to your distant spaceship, you would find that far more time had passed for your crew than for you. Minutes for you might be years for them. You would have traveled into their future simply by moving to a place where time flows more slowly. Of course, hovering near a black hole would require an enormous amount of energy to counteract the relentless pull of gravity, and if you fell past the horizon, there would be no returning. The time dilation would become infinite at the horizon, from the outside perspective, and beyond the horizon, all paths lead inexorably to the singularity. Gravitational time dilation near black holes is not just a theoretical curiosity. It has been observed indirectly in the light from accretion disks, in the orbits of stars near galactic centers, and in the gravitational waves emitted by merging black holes. It is woven into the fabric of spacetime itself, a fundamental feature of how the universe works at its most extreme. In 1974, a young physicist named Stephen Hawking made a startling discovery. He found that black holes are not entirely black. They emit radiation. This was unexpected. According to classical physics, nothing can escape from a black hole. The event horizon is a one-way boundary. Yet Hawking, using principles from quantum mechanics, showed that black holes must radiate energy, slowly, steadily, over immense spans of time. The explanation involves the nature of empty space. In quantum mechanics, the vacuum is not truly empty. It seethes with activity, with pairs of particles and antiparticles constantly popping into existence and annihilating each other in tiny fractions of a second. These are called virtual particles, and they exist everywhere, even near the event horizon of a black hole. Normally, these virtual particles annihilate immediately, and their brief existence goes unnoticed. But near the event horizon, something different can happen. If a particle-antiparticle pair appears right at the horizon, one of them might fall into the black hole while the other escapes. To a distant observer, it looks as if the black hole has emitted a particle. Over time, this process causes the black hole to lose mass very slowly as the escaping particles carry away energy. This radiation is called Hawking radiation, and it is predicted to be thermal, like the glow from a hot object. The temperature of the radiation depends on the black hole's mass. Small black holes are hotter and radiate more intensely. Large black holes are cooler and radiate more slowly. For a black hole with the mass of the Sun, the temperature of Hawking radiation would be only a tiny fraction of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills space. Such a black hole would absorb more energy from the universe than it radiates. It would grow, not shrink. But for a very small black hole, perhaps the mass of a mountain, the temperature would be enormous and the radiation would be intense. Over time, the black hole would evaporate, losing mass, shrinking, and, as it shrank, it would grow hotter and radiate even more intensely. Eventually, it would evaporate completely, disappearing in a final burst of radiation. For stellar mass black holes, the evaporation timescale is unimaginably long, far longer than the current age of the universe. A black hole with the mass of the Sun would take about 10 to the 67th power years to evaporate. Even supermassive black holes, billions of times more massive, would eventually evaporate, but only after 10 to the 100 power years, a timescale so vast it defies comprehension. In the far, far future, long after the stars have burned out and the galaxies have dispersed, black holes may be the last remaining structures in the universe, and even they, given enough time, will fade away, one by one, until nothing is left but faint radiation spreading through an ever-expanding, ever-cooling cosmos. Hawking radiation has never been directly observed. It is far too weak to detect with current technology. But physicists believe it must exist, because it follows from fundamental principles of quantum mechanics and relativity, and its existence raises profound questions. One of the most puzzling is the black hole information paradox. In quantum mechanics, Information cannot be destroyed. It can be scrambled, transformed, hidden, but never lost. Yet, if a black hole evaporates completely through Hawking radiation, what happens to the information about everything that fell into it? The radiation, as Hawking originally calculated it, is thermal and random, carrying no information. It seems as if the information has vanished. This contradiction troubled physicists for decades. Hawking himself initially believed that information was lost in black holes, a violation of quantum mechanics. But most physicists felt that this could not be the right answer. Information must be preserved somehow. Recent work suggests that the information is not lost, but is instead encoded in subtle correlations in the Hawking radiation. As the black hole evaporates, the radiation gradually becomes less random and more information-rich. By the time the black hole has completely evaporated, all the information has been carried away, hidden in patterns too complex for us to easily detect. This resolution, if correct, preserves the principles of quantum mechanics. But it requires a deep connection between gravity and quantum information that we are only beginning to understand. Hawking radiation also suggests that black holes have temperature and entropy, thermodynamic properties usually associated with systems made of many particles. The entropy of a black hole is proportional to the area of its event horizon, a relationship known as the Bekenstein-Hawking formula. This hints at a deeper connection between gravity, thermodynamics, and information. Connections that may point the way toward a quantum theory of gravity. Some physicists have even proposed that the universe itself might be a kind of hologram, with all the information in a volume of space encoded on its boundary, much as the information inside a black hole is encoded on its event horizon. These are speculative ideas, still being explored, but they show how the study of black holes pushes us toward new ways of thinking about reality itself. Hawking radiation remains one of the most beautiful predictions in theoretical physics, a bridge between the quantum world and the gravitational world, between the very small and the very large. It tells us that black holes are not eternal prisons, but temporary structures that will eventually return their borrowed energy to the universe. It suggests that even the darkest objects have a faint glow, if we could only see it. And it reminds us that the universe is stranger than we imagine, that at the boundaries of our knowledge, where quantum mechanics meets general relativity, nature has surprises waiting. At the heart of nearly every large galaxy lies a supermassive black hole. This is not speculation. It is observation, confirmed through decades of careful study. In our own Milky Way, astronomers have tracked stars orbiting an invisible point at the galactic center, moving at speeds exceeding 5,000 kilometers per second, whipping around in elliptical orbits that take them close to something with immense gravitational pull. That something is Sagittarius A*, a black hole of about 4 million solar masses, sitting 26,000 light-years from Earth. The discovery of supermassive black holes in galactic centers was not immediate. For much of the 20th century, astronomers observed strange, intensely bright objects in the distant universe called quasars. These were among the most luminous objects known, outshining entire galaxies, yet concentrated in regions smaller than our solar system. What could produce such enormous energy in such a small space? In the early 1970 seconds, astronomers Donald Lynden Bell and Martin Rees proposed an answer. A supermassive black hole, they suggested, accreting matter from its surroundings. The infalling gas would heat up, releasing vast amounts of energy as radiation. This model explained not only the brightness of quasars but also their other unusual properties, their variability, their broad emission lines, their powerful jets. Over time, it became clear that quasars were not a separate class of object, but simply galaxies with very active supermassive black holes at their centers. When the black hole is actively feeding, accreting large amounts of gas and shining brightly, we see a quasar, or an active galactic nucleus. When it is quiescent, consuming little, the galaxy appears normal, like our Milky Way. The connection between black holes and galaxies runs deeper than simply hosting one another. The mass of the supermassive black hole at a galaxy's center correlates with properties of the galaxy itself. Larger, more massive galaxies tend to have larger black holes. There is a relationship between the black hole's mass and the velocity dispersion of stars in the galaxy's central bulge, a measure of how fast stars are moving. This relationship is remarkably tight, suggesting that the black hole and the galaxy co-evolve, influencing each other's growth. But how can a black hole, so tiny compared to its host galaxy, affect the galaxy as a whole? The answer lies in feedback. When a supermassive black hole accretes matter, it does not do so quietly. The infalling gas forms an accretion disk, spiraling inward, heating up, and emitting intense radiation. Some of this matter is not swallowed by the black hole but is instead expelled, blown outward by radiation pressure and magnetic fields, forming jets and winds that stream away from the black hole at velocities approaching the speed of light. These outflows carry enormous energy and momentum. As they plow through the surrounding gas, they heat it, push it, stir it, sometimes even expel it from the galaxy entirely. This process, called AGN feedback, for active galactic nucleus feedback, can have profound effects on star formation. Gas that is heated or expelled cannot collapse to form new stars. The black hole, in this way, regulates its own food supply. By blowing away the gas that feeds it, it shuts off its own accretion, and the galaxy's star formation slows or stops. This feedback may explain why the most massive galaxies are often red and dead, filled with old stars, but forming few new ones. Their supermassive black holes may have shut down star formation billions of years ago, leaving behind elliptical galaxies that glow with the light of ancient stars. Computer simulations of galaxy formation now routinely include supermassive black holes and their feedback effects. Without feedback, simulated galaxies grow too large, forming too many stars. With feedback, the simulations match observations much better, producing galaxies with the right mix of sizes, colors, and star formation rates. The relationship between black holes and galaxies is not one way. Galaxies also affect their black holes. When galaxies merge, as they often do, their central black holes eventually sink to the center of the merged galaxy and spiral together. These black hole mergers are among the most powerful events in the universe, releasing more energy in gravitational waves than all the stars in the observable universe emit in light during the same time. The first detection of gravitational waves by LIGO in 2015 came from the merger of two stellar mass black holes. Since then, dozens more have been detected, including several involving intermediate mass black holes. Future detectors, both on Earth and in space, will be sensitive to the gravitational waves from supermassive black hole mergers, opening a new window onto the growth and evolution of galaxies across cosmic time. Galaxy mergers also funnel gas toward the centers of galaxies, feeding the supermassive black holes and triggering episodes of intense activity. This is one reason why some galaxies have active galactic nuclei while others do not. The availability of gas, the history of mergers, and the current state of the black hole all play a role in determining whether a galaxy's core is bright and active or dark and quiet. In our own Milky Way, Sagittarius A times is relatively quiet. It accretes only a small amount of material, glowing faintly in radio waves and X-rays. But there is evidence that it was more active in the past. Giant bubbles of gamma rays, called the Fermi bubbles, extend tens of thousands of light years above and below the galactic plane, possibly remnants of an outburst from Sagittarius A times millions of years ago. And the black hole is not entirely dormant. Occasionally, a cloud of gas or a star ventures too close, and Sagittarius A times flares briefly, brightening in X-rays for hours or days before fading again. These flares offer glimpses of the processes happening near the event horizon. The swirling motions of superheated gas, the magnetic fields that channel and accelerate particles, the final moments before matter crosses the point of no return. Supermassive black holes, then, are not passive occupants of galactic centers. They are active participants in galaxy evolution, shaping the distribution of gas and stars, regulating star formation, and leaving imprints on the structure of the cosmos that we are only beginning to decode. They are engines of creation and destruction, feeding on the matter around them, yet also giving back, in the form of jets and winds and radiation, energy that spreads through the galaxy and beyond. They are, in a very real sense, the beating hearts of galaxies, silent most of the time, but capable of thunderous outbursts that reshape their surroundings. And they remind us that even in the darkest corners of the universe, where gravity reigns supreme and light cannot escape, there is connection, influence, and an ongoing conversation between the largest structures and the smallest, between the past and the future, between what we know and what we have yet to discover. For all we have learned about black holes, much remains unknown. We do not know what happens at the singularity. General relativity predicts that space-time curvature becomes infinite there, that density becomes infinite, that the laws of physics break down. But most physicists believe this is a sign that general relativity is incomplete, that at such extreme scales, quantum effects must become important. We need a theory of quantum gravity to understand what really happens at the center of a black hole, whether the singularity is a true point of infinite density or whether quantum mechanics smooths it out into something else. Perhaps a region of incredibly high but finite density, or even a gateway to another region of space-time, remains an open question. Several approaches to quantum gravity have been proposed. String theory suggests that the fundamental building blocks of nature are not particles, but tiny vibrating strings, and that space-time itself emerges from the interactions of these strings. Loop quantum gravity takes a different approach, quantizing space-time itself, suggesting that space and time are made of discrete units, like atoms, at the smallest scales. Each theory offers different predictions for what happens at the singularity, but none have been confirmed by observation. Black holes, inaccessible as they are, remain the ultimate laboratories for testing these central ideas. We do not fully understand how supermassive black holes form. How do black holes of millions or billions of solar masses come into existence? Do they start small and grow over time, or do they form large from the beginning? Observations of quasars in the very early universe, less than 1 billion years after the Big Bang, suggest that supermassive black holes grew very quickly, perhaps too quickly for standard accretion to explain. Either the seed black holes were larger than we thought, or they accreted matter at rates higher than theoretical models predict. Or perhaps both. Direct collapse of massive gas clouds in the early universe could produce black holes of tens of thousands of solar masses in a single event, providing larger seeds that could grow into supermassive black holes more easily. But the conditions required for direct collapse are extreme, and it is not clear how often they occurred. Alternatively, dense clusters of stars in the early universe might have undergone runaway collisions, forming very massive stars that collapsed into intermediate mass black holes, which then merged and grew. Sorting out which mechanism dominated, or whether multiple pathways contributed, will require more observations of the early universe, more detailed simulations, and perhaps new physics. We do not know whether black holes destroy information or preserve it. The information paradox, despite decades of work, remains unsolved in a definitive way. The latest research suggests that information is preserved, encoded in subtle correlations in the Hawking radiation, but the details of how this encoding happens are still being worked out. Resolving the paradox may require understanding the quantum structure of spacetime, the nature of entanglement, and the relationship between gravity and information in ways we have not yet imagined. We do not know if black holes are truly black or if they have structure at the horizon. Some theories suggest that the event horizon is not a smooth, featureless boundary, but a region with complex quantum structure, sometimes called a firewall, where infalling matter encounters a wall of high-energy radiation. Others suggest that the horizon is smooth, as general relativity predicts, but that information is encoded there in ways we do not yet understand. These ideas are still speculative, and testing them will be extraordinarily difficult. We do not know the ultimate fate of black holes. In the unimaginably distant future, if the universe continues to expand and cool, black holes will be the last remaining structures. They will evaporate through Hawking radiation, one by one, until even the most massive have faded away. But what happens in the final moments of evaporation? Does the black hole simply vanish, leaving only radiation? Or does it leave behind a remnant, a tiny stable object containing the information of everything that fell in? Or does something else happen, something we cannot yet predict? The final moments of a black hole's life may hold clues to the deepest questions of physics. We do not know if there are other types of black holes we have not yet discovered. Primordial black holes remain hypothetical. Intermediate mass black holes are only beginning to be confirmed. Are there even larger black holes, ultramassive black holes with masses of 100 billion suns or more? Are there black holes in other dimensions, if extra dimensions exist as some theories suggest? Are there black holes with properties we have not yet imagined? We do not know everything that falls into black holes. Once something crosses the event horizon, we lose all information about it, except for its contribution to the black hole's mass, charge, and spin. What happens to the particles, the atoms, the light, the information? Is it truly lost to the outside universe, or is it somehow accessible through indirect means? Can we ever truly probe the interior of a black hole, or will it remain forever hidden? And we do not know if black holes might be something other than we think. Some alternative theories of gravity predict objects similar to black holes but without event horizons, sometimes called dark stars or gravastars or other exotic configurations. These objects would be observationally similar to black holes in many ways, but fundamentally different in their internal structure. Distinguishing between them requires precise measurements of gravitational waves, of light bending near the horizon, of the shadows cast by black holes. As our observations become more refined, we may find that black holes are even stranger than we currently believe. Or we may confirm that general relativity's predictions hold even in these extreme conditions. These unknowns are not failings, they are invitations. Every mystery is a doorway, a question waiting for someone curious enough, patient enough, creative enough to seek an answer. Black holes have already taught us so much about gravity, time, space, and the nature of matter. They have confirmed predictions made a century ago and surprised us with phenomena no one anticipated. And they will continue to be a source of discovery, a testing ground for new ideas, a reminder that the universe is deeper and richer than any single theory can capture. In the coming decades, new telescopes will map the universe in gravitational waves, detecting black hole mergers across cosmic distances and times. New X-ray observatories will peer at the hot gas swirling near event horizons, measuring the spin of black holes and the behavior of matter in extreme gravity. New radio arrays will image event horizons with even greater precision, perhaps revealing structure, motion, or unexpected features. And new theoretical insights from quantum gravity, from cosmology, from mathematics will deepen our understanding and open new lines of inquiry. Black holes are not the end of physics, they are a beginning. A place where our current theories meet their limits and where new physics must emerge. They are laboratories where nature performs experiments we could never reproduce. pushing matter and energy to conditions that exist nowhere else. They are teachers, patiently showing us what happens when space-time is curved to its breaking point, when time slows to a crawl, when gravity becomes the dominant force in the universe. And they are, above all, reminders of how much we have yet to learn, how much remains unexplored, how many wonders lie waiting in the darkness between the stars. Tonight, as you drift towards sleep, you are floating in a universe filled with black holes. There may be 100 million of them in our galaxy alone, most invisible, wandering quietly through space, remnants of stars that died long before the Earth was born. At the center of our galaxy, 26,000 light-years away, Sagittarius A Times spins silently, a giant 4 million times the mass of the Sun, surrounded by a swirling disk of gas that glows faintly in the dark. Beyond our galaxy, in the centers of billions of others, supermassive black holes wait, some dormant, some blazing as quasars, lighting up the cosmos with the energy of entire galaxies, concentrated in a region smaller than our solar system. These objects, born from the collapse of stars, from the mergers of galaxies, from the strange physics of the early universe, shape the structure of everything around them. They regulate star formation. They sculpt galaxies. They send jets streaming across intergalactic space. They warp time and bend light and emit whispers of radiation that will, in the far future, carry their mass away until nothing remains but the faint echo of their existence. You are made of atoms forged in stars, atoms that were scattered into space when those stars died, perhaps in supernova explosions, perhaps in the quiet winds of red giants. Some of those stars may have left black holes behind. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stellar furnaces and then released into the cosmos. And some of it may have once orbited close to a black hole, swirling in an accretion disk, glowing with the heat of friction and gravity, before being expelled back into space to eventually find its way into the cloud that formed the Sun, the Earth, and you. There is a connection, faint but real, between you and the darkest objects in the universe. You are both children of stars. You are both subject to the same laws of physics, the same curvature of space-time, the same dance of matter and energy that has been unfolding since the beginning. As you rest, the universe continues. Stars burn, planets orbit, black holes spin in the dark. Light from distant galaxies crosses the void, carrying images of the past, showing us the universe as it was billions of years ago, when black holes were young and quasars blazed in the primordial night. And in laboratories and observatories around the world, scientists continue the work of understanding. They build detectors to sense gravitational waves. They track stars orbiting galactic centers. They image event horizons. They run simulations on supercomputers, testing theories, making predictions, comparing them with observations. They write equations, seeking to unify gravity and quantum mechanics, searching for the laws that govern the singularity, the rules that describe the interior of a black hole. Slowly, step by step, we are learning. Not everything, not yet, but more than we knew yesterday, more than we knew a year ago, more than Einstein knew, or Schwarzschild, or Hawking. The work continues, the questions deepen, and the mysteries, rather than disappearing, reveal new layers, new puzzles, new wonders. Black holes are edges, edges of space-time, edges of knowledge, edges of what we can observe and what we can only infer. They mark the boundaries of the known, the places where our maps end and the unknown begins. But boundaries are not walls. They are horizons, lines that recede as we approach, always inviting us forward, always suggesting that there is more beyond. Tonight, you can rest. You do not need to solve these mysteries. Others will carry that work forward. You can simply let your mind wander through the ideas, the images, the possibilities. You can imagine the quiet darkness of an event horizon, The slow spiral of an accretion disk, the sudden brightness of a tidal disruption, the patient evaporation of a black hole over eons beyond imagining. You can think of time slowing, of light bending, of matter compressed beyond recognition. You can picture the galaxy, our island of stars, with its hidden heart, a black hole that has been there for billions of years and will remain for billions more, shaping, influencing, quietly pulling on everything around it. And you can let these thoughts settle, like dust, like starlight, like the soft whisper of radiation from the edge of darkness. Let them drift through your mind, unforced, unhurried, a gentle current carrying you toward rest. The universe is vast. It contains wonders beyond counting. Black holes are among the strangest, the most beautiful, the most profound. They are objects that should not exist, according to our intuition. Yet they do. They are places where the rules of the universe are stretched to their limits. Yet the universe does not break. It simply reveals itself more fully, showing us aspects of reality we never imagined. If these explorations have helped you unwind, if they have given you something beautiful to contemplate as you drift toward sleep, then the journey has served its purpose. Consider subscribing to Dreamly Sleep Space, where we explore the wonders of the cosmos, the mysteries of nature, and the quiet beauty of understanding. Each episode is an invitation to rest, to learn, to let curiosity carry you into the night. For now, let go. Let your thoughts soften. Let the images fade. You are safe. You are resting. And somewhere out there, in the vastness of space, a black hole spins silently in the dark, a monument to gravity, a mystery waiting, a reminder that the universe is stranger and more beautiful than we ever dreamed. Good night, sleep well, and may you dream beneath the quiet stars.